So on problem number 61, you had a reaction. The reaction that it showed was 4Fe2 plus O2. It was a electrochemical cell, and what you're trying to do is you're trying to figure out the voltage produced. In the first part of the question, they're asking for it under standard conditions. So there's the reaction, and if they're asking for it under standard conditions, that would be E naught cell, and you would be calculating the voltage. Well, what I like to do is I like to figure out E cell standard. You should always break it down into two half reactions. Remember, redox reactions, oil rig, oxidation is loss, reduction is gain of electrons. So this one, Fe2 plus is going to Fe3 plus. It is losing electrons, so this is my oxidation. So for oxidation, it's going to be the Fe2 plus going to Fe3 plus, and it has lost a single electron. Now, since we're looking up the standard, we can go to our table. So we go to the table and we look for a reaction showing Fe2 plus and Fe3 plus. So I look, and it's somewhere on here, and it's right there. But do you guys see how it's backwards? That's because this is half reactions for standard reduction potentials, not oxidation potentials. So this is for reduction, but it's the same reaction that I have right here. So what I'm going to do is I'm going to take this number, the Fe2 plus, where is it? Fe3 plus one negative electron produces Fe2 plus, and it's 0.77. To figure it out for oxidation, you flip it. So the sign becomes negative 0.77. I do it different than the book. I take the oxidation and add it to the reduction potentials, and then I figure out my E cell. So I figured it out for oxidation. Now I'm going to figure it out for reduction. To figure it out for reduction, I'm going to again write it out, and it's O2 plus 4H plus going to 2H2OL. Are there any questions about that so far? All right, I looked that up, and I see it right here. And it's written out exactly the way that it is. Only difference is I haven't written out my 4 electrons. So its voltage is 1.23. So it's 1.23 volts. So what I like to do is I like to just add the E cells. So add the oxidation potential to the reduction potential. So I take negative 0.77 volts plus 1.23 volts. And when I do that, I get an answer, which I did ahead of time, which is 0.46 volts. That's the voltage of your electrochemical cell, your voltaic cell, under standard conditions. That is assuming all the concentrations are exactly the same and that it is done at 25 degrees Celsius. Then they throw a wrench into it. They want you to figure out the voltage, which we sometimes refer to as EMF, which is electromotive force. We're going to figure that out for E cell. That's part B, and that's the hard part. We're going to try and figure out how many volts that is. So for B, what I'm going to do is I'm going to write out the Nernst equation. The Nernst equation is what you should always use. So the Nernst equation in your formula sheet looks like this. It is E cell equals E cell under standard conditions minus RT n Faraday's constant natural log of Q. There is another way to write it out, a way that I actually prefer to write it out, that is here, so you don't have to plug in your R or your F. It's kind of a pain to plug in R and F. So instead, you could also have written it out as E naught cell is equal to, or E naught cell minus 0.0592 over N log of Q. Okay, and that's what we're going to use, because then I don't have to plug in my F, and I don't have to plug in my R, and I don't have to plug in my T. So all I need to know to get this correct, we already know our E cell. So the EMF under standard conditions is from part A, and it's 0.46 volts. So the only thing I have to solve for to get this right is to know the number of moles of electrons transferred, and I need to solve for Q. Well, N in this problem is going to be 4 electrons. Did you guys see, there's a shortcut for figuring out how n is 4 electrons. That's kind of a tough thing to figure out. See, you've got a bunch of stoichiometric ratios, and really there's an electron transfer. What's happening is that you've got this, the water, being reduced, and then you have the iron being oxidized. So how many electrons are going between the two? Well, you can actually look at just one of them. And the reduction, see how when I figured this out, it's written out exactly as it is up here. On your standard reduction potential table, look for water. How many electrons are being added to these two to make water? 4. So it's 4 moles of electrons that are on the left side of my reaction. So N in this problem is going to be 4. So going back to this, it's 4 electrons. That's the way to figure it out. You only have to look at it from a half cell as long as that half cell matches what's in the equation, okay? Because what's here should be 4 electrons, as you could see from here. Now, class, do you have any questions about that? All right, now let's keep moving.
So you always find like an equation that matches an oxidation reduction sheet?
The reduction potential sheet,
Oh,
and then if it matches the reduction potential sheet exactly, and then you see how many electrons are in the reduction potential table, that's your moles of electrons.
Okay.
This one, the reason I did it that way is that this one's a little bit more complex. Sometimes a redox reaction is really easy. I'm just going to show you an easy way to figure out N. An easy way to figure out N was actually the last one we did. It was actually that free response question. Darn. Let me click pause here for a second. That was a complex way of figuring out the number of moles, right? An easier way to figure out the number of moles was this one that we just did for our warm-up. I couldn't come up with it off the top of my head. A lot of times, your half reactions, it'll be really, really obvious what N is. In this one, it should be glaringly obvious that 2 electrons are being transferred from the zinc to the lead. In this case, N would be 2. The reason it's more complex for this reaction is because it's not immediately obvious where all the electrons are going. So I just broke it down and looked at it from a half reaction, and that's how I figured out N was 4. So that's part of why this problem was difficult, and that's why it was a good call for it. Now we have to figure out Q. So Q is always going to be our products over our reactants. So let's write out the products over our reactants. It's Fe 3 plus, and the coefficient's 4, so I have to write it to the power of 4. I'm not writing H2O up here as a product. Why am I not writing H2O as a product, guys? Class, why would I not write this in an... It's a liquid. If it's liquid, you can't, if it's liquid or solid, you don't write it out in the equilibrium expression. If it's aqueous, you do. So, what's aqueous? It's this over Fe2 plus to the power of 4. Then we have O2, right? But the O2, the value that they give you is in pressure. You can use pressure besides concentration. Then you have the concentration of hydrogen ions to the power of 4. So let's again look at this reaction right here. I put this over this. This was in molarity, this is in molarity, that's in molarity, and in the problem they gave you pressure. You can use pressure interchangeably with the concentration. So now what you can do is you can plug in all of your numbers. You know, for Q, they give you the molarity for Fe2 plus. The molarity for Fe2 plus is 0.01, so we're going to take that to the power of 4. Fe2 plus they give you, they tell you it's 1.3 to the power of 4. Pressure of oxygen they give you, it's 0.5 atmospheres. Concentration of hydrogen, they don't actually give you the concentration of hydrogen. We have to figure that out. They do, however, give you the pH. The pH is 3.5. Remember that pH is equal to the negative log of hydrogen ion concentration. As Trevor was just pointing out to me, there was a question on the multiple choice practice test that I gave you that had you do a problem exactly like this, where you had 3.5 equal to the negative log of H plus. So what we have to do is we have to figure out what H plus is. So you have to take the anti-log of 3.5, it's base 10, So it's basically 10 to the power of negative 3.5, which is what I think you did in your head, Trevor, when you answered that question. When you do that, you get a concentration of hydrogen ions, I did this ahead of time, as 3.2 times 10 to the negative fourth. And because hydrogen ions are to the power of 4, there's my power of 4. When I do all of this math, Q ends up being 7 times 10 to the fifth. So now I'm ready to solve my problem. I'm going to put a red box around the numbers we need. We need this one, we need this one, and then we need this equation. So what we're going to do is we're going to take Q, put it in there. We're going to take 4, put it in there, and solve for E cell. Do you guys have any questions about how to approach that problem? Anything at all? All right, I want to stop.